Welcome to my presentation about functional structural plant models. My name is Andrea Schnepf, and with this video I would like to elaborate on the mathematical representation of flow and transport processes in this type of models. For modeling flow, transport and reaction in the plant soil system, we consider two spatial domains, namely the plant architecture and the soil in which the roots are embedded. In each of the domains, the balance equation for any given variable of interest, like water potential or carbon concentration, can be expressed mathematically by this partial differential equation. It consists of three terms. The first term represents the change in storage, say of water or carbon. The second term is the divergence of flux. In absence of any sinks or sources, this tells us that this change in storage in any given small volume of the domain is equal to the net flux in or out of this volume. In addition, we have a source term that can represent, for example, water uptake by roots or carbon loading and unloading. Suitable initial and boundary conditions complete the definition of the mathematical problem. Multiple biophysical processes would be described by a system of such partial differential equations, and the source term could then include reaction terms of multiple components. Spatial discretization enables us to solve the partial differential equations numerically. The divergence of the flux is now represented in terms of these two matrices A and C that I will elaborate on in the following slides. The right-hand side term now represents the source terms and the boundary conditions. I will now use terms from graph theory to explain the matrix A, because the underlying concept can be nicely applied to both the soil and the plant domains. In graph theory, this matrix A is called the incidence matrix. As a simple example, let us consider a small plant with one branch and subdivide it into 5 nodes that are connected by 5 edges of length delta x. This is a simple mathematical graph. Let the graph also be a directed graph, so that the direction of each edge is positive in the direction of the arrow and otherwise negative. For each graph, the corresponding incidence matrix is created by setting up a matrix of the size of the number of edges times the number of nodes. In our example, the matrix is of size 4 by 5, and each row corresponds to an edge, and each column corresponds to a node. For each edge or row, we now denote by -1 if the edge is leaving the node, and by +1 if the edge is arriving at a node. In our example, edge 1 leaves node 1 and arrives in node 2. Edge 3 leaves node 2 and arrives in node 4. We can then also write down the transpose of A by converting rows into columns. When we multiply A transpose with A, we get a 5 by 5 matrix that is called the discrete Laplacian. It is our discrete representation of the divergence operator. In the case when there are no branches, it would have this famous tridiagonal form. If we multiply our incidence matrix with a vector that gives the value of our state variables for each node, so we have values for U1, U2 and U up to U5, that could be water potentials, carbon or nutrient concentrations, we arrive at a vector that gives the difference between variables for each edge. You can convince yourselves that this holds also for the branch, so for edge 2, we get the difference between U3 and U2, and for edge 3 that connects nodes 2 and 4, we get U4 minus U2. Next, multiplying the variable differences with a diagonal matrix C of constants for each edge, we arrive at the flow across each edge. This now describes the fundamental physical laws for any gradient-driven flow. This could be Darcy's law for water flow, Fick's law of diffusion, or Ohm's law for electrical current. In the case of Darcy's law, for example, the constant c would include a term 1 over the edge length to arrive from a difference to a gradient of water potential and the hydraulic conductivity. Multiplying the vector of flow for each edge with the transpose of the incidence matrix gives Kirchhoff's law, stating that at equilibrium the net flow in each node must equal to 0. In other words, the divergence is equal to 0. Note that the length of the new vector is now equal to the number of nodes. In our example, it is of length 5. Consider, for example, node 4, where we have the flow of edge 3 arriving and the flow of edge 4 leaving node 4. This is represented here in row 4, where we have the flux of edge 3 arriving in node 4 minus the flux of edge 4 leaving node 4. 3 edges are connected in node 2. Thus, we have 3 flow terms for each of the edges with corresponding minus or plus signs relative to the direction of the edge. If the arrow points towards the node, we have a plus sign. If it points away from the node, we have a minus sign. Returning to our original problem, we can now interpret the spatial discretization as the product of the incidence matrix with U that gives us the difference of U. Left multiplication with the matrix C gives the flow of equations, and multiplying this with the transpose of the incidence matrix gives us Kirchhoff's law at equilibrium. In dynamic problems, it is the discrete divergence operator. The boundary conditions could, for example, represent transpiration boundary conditions for water flow. The source terms could, for example, represent coupling between the soil and the root domains, as for the exchange of water and nutrients, or loading and unloading of carbon in the phloem. With this, I would like to thank you for your attention.